What we have here is a general radio 1232A tuned amplifier and null detector. This one's a fairly rare instrument in the sense that I haven't seen this around that much, and not too many videos on YouTube either. I'm sure there are people who have looked at this and done some work on it, but it's pretty rare to find this in general use. So I just wanted to demo this unit and to show how incredibly accurate it is in terms of its filter characteristics. It's got a very narrow bandwidth bandpass filter. Before we go into the detailed demo for this unit, just to present some information about the filter that is used in this instrument. And this is the Hall network, which is a notch filter in this particular representation. And if you take two paths, one is a straight path and a notch, and you subtract the two, you'll basically get a bandpass characteristic. So this is the principle of the operation for this particular instrument. Intuitively looking at this, at very low frequencies, the signal will pass through the upper resistor, which is shown as 1 plus k times 1 plus 2k over k times r. And at very high frequency, the signal will actually pass through the capacitor network in series. And at some frequency in between, at the notch frequency, I think part of the signal gets shunted to ground, and the phase of that signal becomes opposite to what is going in the forward path, and so that cancels out. So there's a detailed paper on this Hall network filter by Kenneth Kuhn, and I will put the link below in the description, so you could take a look at that and maybe do a future video or presentation on the simulation of this filter, which is very interesting. You need a few amplifiers around this to make it a true bandpass. But I'll stop here at this point to go on with the demo and talk about the theory of this filter a little bit later. And right now what I've got is a 1 kilohertz signal at 10 millivolts RMS being generated by a synthesizer sine wave that's going into this unit. I've got a full 100% deflection or 0 dB, and according to the manual I should be getting a 1.4 volt or so signal on the output, which is basically what this HP 3400A RMS meter is reading. So we are right at 1.42 or so volts RMS. And one thing we can now look at is the ability of this instrument to reject out of band signals. So we can look at that, we can try that by applying a slightly different frequency and see what the deflection happens in terms of the reading change on this meter and also on the HP. So if I apply so to measure the Q of this filter, one has to basically apply a frequency that is off from the center frequency and measure the 3 dB point in either side for a bandpass filter. So let's do that first. I already have tested this before, so I know the 3 dB point, so I'm going to apply that frequency right now. On the low side it's going to be 983 Hertz. As you can see now, the output is around 0.7 or minus 3 dB on the dB scale, and on the RMS meter the output has fallen to around 1 volt. So it has drifted a little bit from when I adjusted it earlier, but it's basically off by 3 dB or so. Now on the high side it should go to 1019, and as you can see it's the same reading. That means this is the 3 dB on the other side, and the RMS of course will read the same, 1 volt. Back to 1 kilohertz. So at 1 kilohertz we are again at the 100% deflection, 0 dB and 1.4 volt on the HP meter. 1 kilohertz signal at 1 millivolt RMS, and I've adjusted the gain to get the same full scale 100% or 0 dB, and there's still a lot of gain left actually on this dial, so it's 120 dB of range, which is pretty high. The output on the RMS meter is as before 1.4 volts, and now we can check whether the bandwidth has remained the same. So if I go to 983 Hertz, it's down to around minus 3.5 dB, and on the plus side we are at minus 2.5. So it's slightly off center, but it's still giving you the rough 3 dB on either side. So I think the meter is this instrument is fairly accurate in that sense. So if you look at these transistors, they are actually mounted on sockets, and that's one of the problems with this like these two transistors, and this one here and several others. They're all mounted in sockets, which can basically create poor contacts, and that causes the instrument to die or not work sometimes, and I have to go open it up and reseat these transistors sometimes. I haven't thought about yet permanently mounting them, but as long as it seems to work, I don't want to damage the integrity of this nice instrument, so I've left it as it is. Most of the capacitors I have changed, that is all these electrolytics. I left these other capacitors, the high low value capacitors, as it is. They are not likely to be affected over time. So it's actually a very nice instrument. I have reconnected most of the internal wiring because I had some problems when I first got it in terms of contacts and stuff like that. I think the tuning has been pretty good. It's fairly accurate in terms of center frequency, although it's off by maybe 1% or so, which is not bad for this analog instrument. So that's one of the applications of this thing, is to use this as an amplifier. So even a 1 millivolt signal, I can bring it to like a 1 volt very easily. As you can see, the gain has still a lot of gain left beyond. So it's now beyond the full scale. So it's very sensitive in that sense. So here's another application that you can use this null detector and amplifier for, and that is to extract harmonics out of a repetitive signal that is not sinusoidal. In this case, I put in a square wave at let's say 1 kilohertz here, and we'll try and see whether we can extract all the harmonics out of this guy and see what the harmonic content of this particular square wave signal is. So at 1 kilohertz I have a full scale reading. So now the next harmonic is of course second harmonic at 2 kilohertz. So if we go to 2 kilohertz, let's see what happens. Basically there's nothing there. Let me switch to the higher scale. So this is the next higher scale. So at 2 kilohertz, as I expected, there's no harmonics content on the square wave. You should see something at 3 kilohertz. That's basically the first visible harmonic, that is 3 kilohertz. While I won't trust the amplitude of this instrument because it's got some gain variation, because the filter is not perfectly tuned at all frequencies for gain, but still gives you a reasonably good relative amplitude. It's about 18% of the first harmonic. So we'll make a note of these and see if they make sense from an ideal square wave. And then at 4 kilohertz it should be nothing there. And at 5 kilohertz you can see the amplitude is dropped, but there's still about 10% there. Then at 6, nothing. 7th harmonic, it's about 6% or so. 8, 9, you can see a little bit there. and then 10, 11, there's some deflection, and these get progressively weaker and weaker. So 13th harmonic barely moves, but actually I can bring that up to a fairly strong level by increasing the gain. So this is that's even I can get a full 1 volt signal out of this at the 13th harmonic, and if I tune this precisely, I should be able to maximize the frequency. So this is about where the 13th harmonic is picking up the full scale, and my meter is also showing the same 1.4 1.5 volt amplitude coming out. So this is basically a 1 millivolt square wave, and I'm able to basically extract the 13th harmonic full scale. I can even go higher, I think, the 15th harmonic, even weaker, but I can still bring that back to 200% full scale. This is the 17th harmonic, and still I'm able to bring the 1 volt back in there. So, and I think this will go to the 19th harmonic here, and still I'm able to bring back 100% on this one. So I should be able to go further, but I think it starts to get into the noise level. I shall end here, but you can see how incredible this simple instrument can be in extracting harmonics out of a repetitive signal that has got various components in it. Of course, I could do a signal that has even harmonics as well. This setup shows a 10 kilohertz signal with an amplitude of 10 millivolts RMS, and the output on the HP 3400A is 1.42 volts as before for a full scale reading, and I've actually marked some of these settings approximately to see what kind of gain setting I need to get a full scale reading based on the input. So this is approximately at 10 millivolts, and it's right there. Now if I want to test the 3 dB bandwidth of at this frequency, which is going to be slightly different because the curves are different for different ranges based on the capacitors and settings that are being used. So I believe this has slightly lower Q at this frequency, so let's try 9.6 kilohertz. So we are down to around 56-57%, so I can go a little bit higher. At 9.7 kilohertz I'm almost down to 3 dB. A little bit too high, so 9.72 kilohertz. So about 9.72 kilohertz I have a minus 3 dB, and on the positive side, let's see where we get to. Let's try 10.3. So a little bit too much gain, so 10.65 kilohertz, that's way too low. So at 10.35 kilohertz I've got exactly minus 3 dB as well, so the spread is slightly more than before, maybe around 6%. I'll do the calculation later. So at different standard frequencies, we get slightly different cues, and that is to be expected from this instrument. It's fairly simple instrument which doesn't do much tracking. So this is a fixed 50 kilohertz setting. Of course the dial has no effect on this in this particular setting, and this has looks like the sharpest Q, but we can test that to see where we have what we get. Let's see, 48 kilohertz. Okay, 49 kilohertz. So it looks like 48.5 kilohertz will bring you, or 48 48.7 kilohertz. So about 48.7 is the minus 3 dB point, which is a very sharp drop off. On the other side it should be maybe 51.3. So 51.2 kilohertz is about on the positive side. So it's a very narrow filter. Pretty amazing for something that is so simple in terms of the number of components to get this kind of cue. So to end this video, I'm going to highlight some of the curves which are in the manual. These set of curves show the filter tuning curves at different frequency bands. And as we saw earlier, that at the 10 kilohertz band, we had slightly larger, slightly lower Q or slightly higher bandwidth or spread. And the tightest was actually the 50 kilohertz, which we also measured. So basically, we have to be, we can't get the same exact Q at all the different frequency bands, which is 5% according to the manual, but in some cases it's higher, in some cases lower. The next set of curves actually show the gain variations, and this is significant because once I try to measure the square wave amplitude for the harmonics, I was seeing a lot of variation. As you can see, within each band there's almost like a 6 dB or 7 dB of variation, and so you really can't use this to calculate the harmonic amplitudes accurately unless you can calibrate the instrument at these frequencies and make a note of these and then adjust for those. So this concludes this video on this little known instrument, the GR-1232A null meter and tuned amplifier. Hope you found this interesting. These instruments are available, not very expensive, around $50 to $100. And in the future I might do a video on the theoretical aspects of this, the filter, and how this is actually designed. So hopefully I can get to that later. Thank you.